Can anybody out there on the entire internet explain to you how a computer can do what it does using nothing but ones and zeros? Well, folks, I believe you have come to the right place. Okay, so why does a computer use binary instead of like a normal number system like we're used to? That should be a pretty simple question, right? We're all familiar with a decimal system that's 10 places, because from an early age, we're all born with this reference system right in front of us. That's pretty easy to grasp. And hexadecimal, give me a break. Oh, for God's sakes, So why does a computer have to use a binary to do what it does? Well, the answer for that is because a computer can add together two binary numbers extremely fast. I'm talking like faster than lightning. Of course, any physicist will laugh, and say, no, that is incorrect. Lightning and electricity travel at more or less the same speed, to which I would retort, yes, but in the time it took for this lightning to leave the Earth and enter into the upper atmosphere, and yes, you heard me right, lightning does in fact move from the ground up, believe it or not, in that amount of time, your computer's processor could have easily made 1,000,000 calculations, one at a time. In fact, a modern computer processor, like your x86 64-bit processor, which is most likely what you are running on your computer, otherwise you probably wouldn't have been able to boot into chaos, can do something in the neighborhood of 100 billion executions per second. Wow. Okay. So now what if I told you that all your computer's processor can do is add two numbers together? And I'm not like talking metaphorically or anything. I mean, literally, that is it. All your computer's processor can do is addition between two binary numbers. Well, of course, you're going to immediately wonder, well, yeah, that can't be, because I can open up a calculator on my desktop and do subtraction. If all a computer can do is addition, how is it possible that it can subtract? Well, it's simple. It just adds a negative number. Oh, okay, well, got that. Fair enough. Okay, what about multiplication? How is it possible to do multiplication? Well, just add the same number over and over. Well, okay, well, what about division then? Well, you simply subtract. You keep subtracting till you can't subtract anymore and count the number of times you subtracted. If there's anything left over, you return the remainder, right? And all this is accomplished at such blinding speeds because of your computer's ability to crunch numbers. Now, what does that mean, to crunch or not to crunch, as the case may be? No, whoa, no, oh, wait, oh, no, yeah, good enough. Okay, so yeah, what does that mean when your processor actually crunches binary numbers? Okay, so here's what happens. You got a pair of binary numbers here. In this case, 1 and 2, the values. Okay, so all your processor does, keep in mind, these are just electrical circuits. An electrical circuit that is on, and these are all off. This is just a little charge in there. All your computer does is push this value up here over to the other one like that, right? And what you get is that. There, I've just added 1 and 2, resulting in a binary value of 3. Okay, and then of course it'll just continue. If in this case, if there already happens to be a value in that slot, it'll get canceled out, right? And then it'll just move over to the next slot, right? And then of course if there's another value here, then the same thing, right? Which of course you're familiar with the concept of carrying the 1 in decimal places, right? But the advantage of using a binary system is that it can just move the whole thing over in one chunk. all at one time, you see. So that kind of speeds things up. And of course, keep in mind that electricity can travel around the Earth at approximately 8 times per second. In theory, if it was traveling through something like metal wires or whatever, maybe 7.4 times in 1 second. But still, that's blindingly fast. Yeah, it means the electricity can travel all the way around the Earth, over 24,000 miles in about 1/7 of a second, blinding fast, Today we have fiber optics, which is made out of glass, so now we can transfer information around the world at the speed of light. This, of course, is me blowing glass. Feel free to check out my shop, obligatory plug there. So you know how electricity works. You throw the switch, the electricity flows, goes through some substrate, electrical wires or whatever, keeps going through the wires, la la la. What are you looking at? And finally it reaches its destination, okay? And then, of course, the light bulb goes from black and white to full RGB color. Great, Okay, and then of course there are different types of switches. Like here's a switch where if it's thrown in one direction, it can do one thing, but if it's thrown over here in the other direction, it could be hooked up to do something entirely different, And then of course there are vastly more complexly different types of switches, which I don't really need to go into. We just got to think about switches here for a second. This is your basic schematic diagram if you're familiar with electronics. If you ain't, this is a symbol for a light bulb. Right, this is a symbol for a switch, and then you got some wire here, and trying to send a current through the wire, but it ain't going to flow because it is an open circuit. Right, simple. When the circuit is closed, the electricity can flow through the wire, and the light bulb lights. Okay, now the way your processor works is on the principle of semiconductors. Now, the way a semiconductor works is there's a certain amount of resistance, and that amount of resistance is known. Okay, so if I have a semiconductor in here, and I give it a very small amount of electricity, the electricity will not flow. But if you give it just a little bit more electricity, now the electricity begins to flow. Okay, this is advantageous in the world of computing because this allows you to set up a basic logic circuit where, imagine this is a wire and it can have a current flowing through it, here represented by, there's no current flowing through this wire, but there is current flowing through this wire represented as a 1, you see? And so now I have them both connected to the same semiconductor, and if one of these is a 1, it's not enough electricity to flow. So you end up getting a 0 here. But if both of these are a 1, now that there's enough electricity for it to flow, and bang. That is your basic principle of a semiconductor, and that is the root foundation of all of your modern processors. Of course, there are many different types of semiconductors, but we use silicon. That's part of the carbon family here. We were all basically carbon-based life forms because it's the second most abundant element on the face of the planet, next to oxygen. Right? It is literally everywhere, but you can't just dig up some sand from the beach and make a silicon chip from it. No, you need extremely pure silicon. This is silicon based, it's quartz, which is like 99.9999% silicon, but it's actually silicon oxide, and it's actually a little dirty. It's not pure enough. So you need to purify your silicon like 10 times over to get extremely pure silicon. I mean, completely 100% pure, because we're going to be dealing with very tiny amounts of it, so it has to be 100% free of any impurities, right? Okay, so then you take that silicon and you melt it down at extremely high temperatures, and you pull it out into an ingot, which basically is one of these rods. You just kind of cooler rod, and then you take that one of these rods and you slice it up into these just very thin wafers. Okay, that's maybe the size of a quarter or dime, depending on what size of ingot you were able to get out of there, right? And then you can take a microscopic level, atomic level machine and etch a chip into that wafer. And I remember I said this wafer here is maybe the size of a quarter, and this thing is not making one computer chip. No, you're probably putting 200 chips on this single wafer, which is then cut into slices, and you end up with these little things called dies, and that is the processor on your computer. And then, of course, they do a little bit of testing, rigorous testing, to make sure all the circuits work right. And if one of these, if there's one little logic circuit in there that doesn't work right, well, they take that and they throw it in a box. And then, of course, they sell that to your refurbished computer people. And they take a normal computer, pop out the perfectly good working chip, and pop in one of these faulty ones and sell it to you for $200 cheaper and call it a refurbished computer. So if you ever buy one of these refurbs and wonder why it crashes all the time, now you know. Okay, so here is your actual brain of your computer. Whoa. Here's a processor die. It is the size, roughly 1/6 the size of the little fingernail on your little finger. Yep, believe it or not, your entire computer is run off of this tiny, tiny little thing. Yep, you got this great big computer. It's got all this stuff all hooked up to it, or maybe you got a laptop, but nonetheless, inside there's nothing but this motherboard. They all work the same. And all this electronics, wow, it's just loaded with electronics, but there's your processor right there. And when you look at it, it's like all of this stuff out here is just so you can connect things to your processor. There, you want to put some more RAM in, you want to put some more DRAM in, you want to upgrade the video card, there's a slot for that, you want to plug in a monitor, there's a slot for that, you want to plug in an internet connection, you want to plug in audio, video, HDMI, whatever. You got all this tons of electronics on there. 95% of it is just so you can plug your things into this tiny little processor, and you can pop that out of there, and you can see that there's just tons and tons of little connectors on the back. There's all these pins, and there's tiny little wires coming off, to connect everything to this little bitty thing, and now here's an old Pentium computer. Processor 256K. Wow. 286 computer, whatever. But this thing, this outer case is made of solid gold. I have one as a souvenir. This thing literally has a gram of gold in it. That's right. There is gold in our recycling heaps, folks. And yeah, you can just melt that down. And the reason they did that was because those processors are so tiny that if the slightest bit of rust or tarnish got in there, then it could screw up the whole thing, you see. So you have to use a type of metal that was non-corrosive. Of course, now they found cheaper solutions these days. Here's the back of the processor. You can see all the pins that let you plug it into your motherboard, and it's got the cap removed. Of course, now it's rendered useless. And inside is this tiny little chip, right, with all these tiny little wires coming off that attach to these pins just so you can plug it in. This processor, a couple inches in size or whatever. All of this is just so you can plug the darn thing into something. It's too tiny to be able to plug into something. So you have this interface. Oh, a modern processor. Oh, it's even bigger. And the reason this one is bigger is because it's got 4 processors all built in to a single system, complete with a bunch of cache and onboard video memory and all kinds of stuff, all built into one, And okay, so, and if you got and looked at inside, all of this is inside of that. And if I'm not mistaken, this is just one layer of several or many of what's actually inside there. It just goes endlessly on and on and on. And every one of these is just countless, mind-blowingly endless tiny little circuits. And so the principle of your semiconductor, I showed you, you got a wire and you got a semiconductor in between there. They discovered in the early days that the speed of a processor didn't deal so much with how fast the electricity could move through the semiconductor. No, it was how fast it could move through the wires that connected one thing to another. So what some physicists figured out is like, well, if I had this wire and it goes from here to here, if I was able to cut that distance in half, I would have a processor now that runs twice as fast. And so now the race was on to make smaller and smaller processors. And then, so every couple of years, another processor would come out, and it was half as big and twice as fast. And they went down and down and down until today you're at the level really where this entire processor is composed entirely of silicon. There's no wires connecting anything to anything else. It is back-to-back circuits with like no room for anything else. I mean, literally, we're down to like not a microscopic level, an atomic level, where these circuits are no more than 3 to 12 atoms in size. They have literally like reached the limitations of how fast a computer's processor can be. They started out at 200 megahertz, 300, 400. Now a processor can be a little over 1,000 megahertz fast. So now what they do is they gangbang them. You have like 4 processors. So now, wow, your processor can literally do 4 calculations simultaneously, but still at a maximum speed. And of course, you need programs that can run on a quad processor or whatever to take advantage of all of that power in there. Many of them don't even do that, but it's there. So in theory, so now your processor, your computer's processor can run at 4,000 megahertz instead of 1,000 megahertz, but that's parallel processing, you see. It can do 1,000, it can do four things simultaneously at 1,000 megahertz, you see, which, can have the equivalent of blinding fast speeds, But there you go. That is basically how the state of the art in computer chips works today. They've even, I understand, IBM has just discovered how to store memory in a single atom. Whoa. Mind-blowing, that may or may not affect the size of processors, but that will certainly make your hard drive smaller. What you think of an iPod today or whatever, someday would probably fit on a postage stamp, if not for the fact that you needed to be able to plug something into it. So most of these computers, little tiny mini gum stick computers or whatever, it's like half the size of it is just simply so you can plug things into it. They are so tiny. Yeah, there you go. So I hope I have done a good job of explaining, how your computer actually does what it does under the hood, so now we can get back to actually making it do some cool things. Huh? How's that sound?